A single blade passes overhead, slow, almost lazy. It stretches longer than a football pitch, and at the tip, air screams past at over 300 kilometers per hour. If the blade's angle drifted by even a few degrees, drag would rip through the fiberglass until the whole thing shattered. Everything keeping that blade intact starts with a shape most people never notice, a twist built into the blade itself. From the ground, a wind turbine blade looks like a simple paddle slicing through the air. It isn't. The blade is an airfoil, shaped so that wind traveling over the top surface moves faster than wind passing underneath. That speed difference creates lower pressure above the blade and higher pressure below, and the imbalance pulls the blade upward and forward. The blade doesn't fight the wind grabs it. But lift is only half the battle, because the blade isn't moving at one speed. Near the hub, it barely crawls. At the tip, 80 or 90 meters out, it tears through the air at hundreds of kilometers per hour. Each section of the blade lives in a different wind. Close to the hub, the air feels slow and arrives mostly from the front. At the tip, the blade's own velocity creates an apparent wind so fierce it dominates everything else, hitting the surface at a completely different angle. A single blade experiences two different atmospheres simultaneously, and the airfoil that works perfectly near the root would be catastrophically wrong at the tip. This is where drag finds its opening. If the blade were straight and untwisted, the tip would punch into its apparent wind at the wrong angle. Airflow would separate from the surface, and turbulence would pour in behind it. Drag wouldn't just increase, it would explode. The vibration alone would hammer the fiberglass through millions of stress cycles until the material cracked and the blade tore itself from the hub. The twist prevents it. From root to tip, the blade gradually rotates along its own axis, angling each section to meet the specific wind it actually encounters. The entire blade is a continuous gradient of compromises, every centimeter calibrated to survive a version of the wind that the centimeter beside it will never feel. But keeping the blade alive is only half the problem. The turbine still has to find the wind in the first place. Wind doesn't hold still. It shifts direction dozens of times an hour, sometimes by just a few degrees, sometimes by 90. A turbine pointed even slightly off-axis doesn't just lose power, it loads its blades unevenly. One blade bites into full wind, while another catches almost nothing. That asymmetry sends uneven forces hammering through the hub with every rotation, and over thousands of cycles, uneven forces crack steel. Two instruments stand between the turbine and that slow destruction. Bolted to the back of the nacelle, a housing the size of a city bus, sit an anemometer and a wind vane, each no larger than a human forearm. The anemometer reads speed, the vane reads direction. Together they are the turbine's entire sensory system, the only way a 300-ton machine knows where the wind is coming from. The moment the vane detects a shift, even a few degrees, it sends a signal to a controller that triggers the yaw drives. The yaw drives are electric motors mounted at the base of the nacelle where it meets the tower. They engage a massive toothed ring gear, a steel circle bolted to the top of the tower itself, and begin rotating the entire nacelle. 300,000 pounds of generator, gearbox, shaft, and housing turning on a ring of teeth, steered by two sensors that could fit in a kitchen drawer. The motors don't spin the nacelle once and stop. Wind wanders constantly, so the yaw system hunts constantly, adjusting heading thousands of times a year, through calm days and through storms that try to shove the nacelle sideways faster than the drives can track. Precision keeps the machine alive, drift keeps it dying. The yaw system lives permanently between the two. Once the blades are facing the wind and spinning, all that rotational energy funnels into a single point, a steel shaft turning at a speed that is almost useless. The main shaft turns about 15 times per minute, slow enough to watch. It is a massive steel rod bolted directly to the hub, and it carries enormous torque, the combined rotational force of 3 blades, each longer than a football pitch, driven by tons of moving air. But torque without speed is almost worthless to a generator. At 15 revolutions per minute, the shaft holds raw power in a form that can't produce meaningful electricity. Everything depends on what sits behind it. The gearbox takes that slow, heavy rotation and multiplies it. Through a series of interlocking gear stages, 15 revolutions per minute becomes 1500. The energy doesn't increase. Conservation of energy forbids it, but the character of the motion transforms completely. What enters the gearbox as a slow, massive force exits as something fast, light, and violent. The shaft on the other side is spinning 100 times faster than the one that went in. That transformation comes at a cost. The gearbox is the most mechanically punished component in the entire turbine. Gear teeth absorb thousands of tons of cyclical force, every rotation pressing steel against steel under loads that fluctuate with every gust. Heat builds, lubricant breaks down, metal fatigues at contact points invisible to the naked eye. Gearbox failure is one of the most common and most expensive breakdowns in the wind industry, requiring cranes tall enough to reach the nacelle and repair bills that can run into hundreds of thousands of dollars. The gearbox doesn't just transfer energy, it concentrates all the mechanical violence of the drivetrain into one location. And because the gearbox created that violence, the emergency brake sits right beside it. If a storm drives the blades beyond their safe speed, massive hydraulic calipers slam shut on a steel disc attached to the high-speed shaft, locking the entire drivetrain in seconds. The brake exists specifically because the gearbox turns something slow and manageable into something fast enough to tear the machine apart. But even at 1500 RPM, the energy pouring off that shaft is still raw mechanical motion, and the grid doesn't want motion. It wants electrons, delivered at one exact frequency, with zero tolerance for error. The grid demands exactly 60 Hz, not 59, not 61. Feed it the wrong frequency, and the consequences travel far beyond the turbine. Blackouts cascade through substations, transformers overheat, equipment hundreds of miles away suffers damage it was never built to absorb. The grid doesn't negotiate. It takes what it needs or rejects everything. Inside the nacelle, the generator is a doubly fed induction machine. A rotor wound with copper coils spins inside a stator lined with matching coils. And as the rotor turns, the interaction between their magnetic fields converts mechanical rotation into alternating current. The principle is simple. The reality is brutal. With 4 magnetic poles, the math demands exactly 1,800 revolutions per minute to produce 60 Hz. The gearbox delivers roughly 1,500 revolutions per minute. The wind decides the rest. When a gust dies and the rotor drops to 1,700 revolutions per minute, output falls to 56.67 Hz. Too low. The grid sees contamination. When surges push the rotor to 2,000 revolutions per minute, output jumps to 66.67 Hz. Too high. The grid rejects it just as fast. The margin between useful electricity and waste is measured in single-digit hertz, and the wind respects none of it. A controller fights to close the gap. Through slip rings mounted on the rotor shaft, it injects a separate current into the rotor's copper coils, creating a magnetic field that spins independently of the rotor itself. When the rotor runs too slow, the controller's field spins forward, adding the missing frequency. At 1,700 revolutions per minute, it supplies exactly 3.33 Hz, and the stator output hits 60 Hz. When the rotor overshoots to 2,000 revolutions per minute and produces 6.67 Hz too many, the controller reverses direction, subtracting the excess until the output falls back to 60. The controller never rests. Wind dips, surges, gusts sideways, and every shift changes the rotor speed and the frequency pouring off the generator. hundreds of adjustments per minute, everyone recalculating the gap between what the rotor delivers and what the grid will accept. A permanent argument with a force that refuses to cooperate. If the controller falls behind, if frequency drifts beyond the grid's narrow window, the turbine disconnects entirely. Every watt the blades produce spills into nothing. The argument is one the controller can never permanently win, only keep winning, moment by moment. The frequency holds, the generator delivers, and now the electricity needs to survive a 300-foot drop down the tower's core. Cables thick as a human arm carry the current down through the hollow steel tower. 300 feet of vertical drop, swaying in wind that never stops pushing, inside a structure that rises high enough to attract lightning. The electricity has survived the blade, the gearbox, the generator, and the controller's endless frequency war. Now physics threatens it in a different way. The generator produces roughly 690 volts, enough to power a factory floor. Nowhere near enough to travel any real distance. At 690 volts, the current required to carry meaningful power is enormous, and current generates heat. Send that electricity down a transmission line toward the nearest town, and resistance bleeds it dry. Energy converted to waste heat, mile after mile, until almost nothing useful arrives. The voltage is strong enough to exist, but too weak to survive the journey. At the base of the tower, the transformer intercepts it. The transformer steps 690 volts up to 33,000 or more, and in doing so, it trades high current for high voltage. Less current means less heat. Less heat means less loss. The electricity that couldn't travel 10 miles at 690 volts can now cross an entire region at 33,000. It flows from the tower base into underground cables, reaches a substation where voltage climbs even higher, and finally enters the overhead transmission lines that feed the grid, reaching homes and cities. From a blade twisting to meet wind it cannot see, to a controller fighting a frequency war it can never permanently win, to a transformer rescuing voltage from bleeding out as heat. Every component inside a wind turbine exists because the one before it left a problem unsolved. From the ground, a wind turbine looks like a single clean machine. A white tower, 3 blades, a slow turn against the sky. Nothing about it suggests conflict. But inside, every single component is fighting a problem the component before it created. The blades twist because a straight edge would shatter under its own drag. The yaw system hunts because wind refuses to hold a heading. The gearbox multiplies speed because the shaft is too slow to be useful, and the brake exists because the gearbox made that shaft too fast to be safe. The generator produces electricity the grid would reject, so a controller wages a permanent frequency war on its behalf. The voltage that survives all of it would bleed away as heat without a transformer at the tower's base to rescue it. None of these systems are elegant alone. Each one is a patch, a correction, a compromise forced by physics that refuses to cooperate. From the highway it looks effortless. Inside, engineering is winning by exactly enough, and it has to keep winning with every rotation. The next time you see a turbine from a highway, you're watching a machine arguing with itself since the moment wind started blowing. If you want to see what happens when that argument is with water, when a dam holds back pressure that could flatten a city and the only thing between collapse and control is a single gate weighing more than a locomotive, subscribe and we'll take you inside.